Right, so welcome to Math409 problem solving. And so this is lecture days when we don't have class, reading period or whatnot. So the numbering might be a little bit different than other classes. And so what I want to do today is I want to do complex analysis in a day. So this is an absolutely beautiful subject, an absolutely beautiful class. I gave a problem that one can look at to solve an integral, which is related to a research project I'm mentoring with a student. And I think the way to solve this is to use complex analysis. So it is a great way to do integration without integrating. So out of curiosity, how many people here have not taken a class in complex analysis? Okay, good. So the purpose is to just give you a quick sense of what that class is like without going into rigorous detail about why I can do everything I can do. So this is, we're going to be physicists or even worse, economists today, and just play fast and loose with the math. It can all be justified. So one way to teach the subject is to use Green's theorem. And so I've linked the standard statement. You should have seen this in multivariable calculus. It's in Math 151. If you took Math 150, it is sometimes not covered. I always cover Green's theorem when I teach 150. I feel that if you go through and haven't seen it, you've missed one of the biggest results in calculus. I don't go through the proof in excruciating detail, all the line integrals and whatnot, but essentially what Green's theorem says, and we're not going to do too much with it, but if you know of it, it's a way to justify a lot of what happens. If you have an integral of a function along a curve, and so integrate a function along a curve, at each point on the curve, you have a tangent vector, and you look at your vector valued function, and you take the dot product of the vector valued function with the tangent, so you have a one-dimensional integral. If you want, you can think of it as parametrizing your curves. And it turns out that this one-dimensional integral is equal to a two-dimensional integral. So I'm not going to go into great detail about this. If you're interested, I do have a Green's theorem in a day lecture from when I taught Math 150 so long ago that it wasn't even Math 150, it was Math 105. This was before the Zoom era, and we actually had somebody professionally recording those classes. So again, if you've seen Green's theorem, it's a way to justify a lot of what we're going to do in complex. So the first thing is we need to know, what does it mean for a function to be complex differentiable? Well, hopefully everybody remembers what it means to be differentiable of one variable, of a real variable. It's essentially the same in complex analysis. I want the limit as h goes to 0 of f of z plus h minus f of z over h to exist, and we call it f prime of z. In one dimension, how many ways are there to approach a point in one dimension? Two. It's really boring. You can basically move from the left or you can move from the right. As soon as you are in higher dimensions, if I give you some point z, I can approach along the axes if I want. I could also spiral in, or I could do some kind of strange scribble. The limit has to be the same for all of those. And so to be complex differentiable, it turns out it is significantly stronger than being real differentiable. Another reason to do this lecture today is this is technically a senior seminar where we're supposed to put together all the math you've been seeing. What does it mean for a function to be differentiable of two variables? It's not that the partial derivatives exist. What it means is if you look at the tangent plane approximation, the tangent plane approximation does such a good job that when you subtract that, that still goes to 0. So the generalization we often use is we look at the limit as h goes to 0 of f of x plus h minus f of x minus f prime of x times h over h equals 0.
What is that the generalization of?
Well, I mean, this is still the standard definition of a function to be differentiable of one variable. Because if you think about it, f prime of x times h over h is just f prime of x. And so if this whole thing equals 0, that's the same as just moving f prime of x to the other side. So in several variables, the way this generalizes is it would be the limit as the vector h goes to 0 of f of, let's say, x plus h minus f of x minus the gradient of f at x dotted with h over the length of h, and I'll do, the length of the absolute value of this goes to 0. That is the correct definition of being differentiable in several variables. How many people have seen this as the definition of differentiability of several variables? Okay, good. But I'm not seeing every hand go up. So this means you've taken multivariable calculus, you've manipulated things, you've differentiated things, but you have not had a proper definition of what does it mean. There are functions where the partial derivatives all exist, but the function is not differentiable. So you have to be extremely careful. All right, so for the most part, things hold as you would expect. I'm not going to go into too much detail. There is something called the Cauchy-Riemann equations. If I give you a function f of a complex variable, we often write z as x plus iy. And so I can write f as its real part plus its imaginary part. And so we typically use u for the real part and v for the imaginary part. And it turns out if the function is complex differentiable, then u and v satisfy these relations. So let's try to think of some interesting functions to see if they're differentiable. Can somebody give me a function of a complex variable and we'll see if it's differentiable? Simplest one you can think of. F of z equals 0. We can even extend it slightly to f of z is 1 or any constant. So if you take any constant, then clearly f of z plus h minus f of z will be, what would that be? If you take f to be constant, what will the derivative of a constant be? 0. And so u would be 0, v would be 0, Cauchy-Riemann equations would be satisfied. What's the next simplest function we could take? F of z equals z, and after f of z equals z, what could we take? Z squared. So let's do f of z equals z squared. So we'll take f of z is z squared. So f of z plus h would be z squared plus 2zh plus h squared. So f prime of z would be the limit as h goes to 0 of f of z plus h minus f of z over h. So this is going to just be the limit as h goes to 0. The z squares cancel. We have 2zh plus h squared over h. The h's cancel and we'll just get 2z. So this function is differentiable. So in this case, if f of z is z squared, so that means f of x plus iy is x plus iy squared. This is going to be x squared minus y squared plus 2ixy. So what would u of xy be and what would v of xy be? So u would be x squared minus y squared and v would be almost just 2xy. And so here is an example of a differentiable function. You can show it satisfies the Cauchy-Riemann equations.
And why is v of xy 2xy?
Well, because we're writing f as u plus iv. So if I calculate, it's x squared minus y squared plus 2ixy. So my v is going to be just be, you take out the, and this way u and v are real valued functions. And so you can do the differentiation. You can see du dx equals dv dy, and du dy equals negative dv dx. So you can check that the Cauchy-Riemann equations hold in this case. The reason that this can be used for complex analysis is if we go back to Green's theorem, this line integral, this one-dimensional integral is very easy if dm dx minus dl dy equals what? What would be a wonderful thing for this to equal? If this equals a certain number, if it equals 0, the line integral is trivial to do, right? If you do an area integral of 0, what do you get? You just get 0. So how many of you have done physics? So they often talk about if you have a closed path and you return to where you start, in a conservative field, there's no net work done. And that is essentially coming from an integral like this, that if this integral is 0, no work was done. And it turns out if your function is complex differentiable, this du dx equals dv dy, when you split everything up, it's essentially telling you that those area integrals are 0, so the line integrals are 0. This is going to allow us to convert integration to algebra. For a function that's not complex, so this is complex differentiable, exercise f of z equals z bar, which is x minus iy, is not. It's just always good to know what, at least one example that is and at least one example that is not. With a little bit of work, using mathematical induction, you can show that z to the n is differentiable for any positive integer n. And then you can show that any finite sum, any finite linear combination of z to the n's is differentiable. And then you wave your magic wand and say, in certain circumstances, if the series converges, the infinite sum is differentiable, and we can work with that. We are not going to worry about infinite sums and convergence. We're going to just barrel ahead. So the next thing is just a quick motivation as to why is all of this useful? Well, imagine I give you a polynomial. So I can write my polynomial, I can pull out the leading term, and then I have coefficients. Well, if I know the roots, does everyone agree that if I know the roots, I can figure out what the coefficients of the polynomial are? We just multiply everything out. We should be able to go in the other direction. If I know the coefficients, I should be able to determine the roots up to some kind of ordering. And so there are formulas that allow you to do this. If the degree of the polynomial is at most 4, we have explicit formulas. We don't have general formulas once the polynomial is of degree 5 and higher. And we have to resort to things like Newton's method or whatnot. But the idea is frequently knowledge of in one area translates to knowledge of another. We've seen this with generating functions. We saw this with the Riemann zeta function, that we could pass from knowledge of the integers to knowledge of the primes. And the idea is frequently, if we know things about the coefficients, that gives us information about the zeros. Or if we know things about the zeros, we then know things about the coefficients.
Question.
Yes.
What's the last note? It says for like C of S, the coefficients are related to primes.
For zeta of S.
Yeah.
So if I look at polynomials involving the Riemann zeta function, we have a connection between the integers and the primes. So it turns out if you know things about the distribution of the zeros of the Riemann zeta function, that gives you information about the primes. You have to do a logarithmic transform because we have this Euler product that says the Riemann zeta function, initially defined as a sum over integers, is also equal to a product over primes. We don't like to work with products. We like to work with sums. But the log of a product is the sum of the logs. So if we take a logarithm, we now have the log of the zeta function, which will have a series expansion involving primes. And by knowing things about the zeros there, we can translate information about the primes. So what I want to do today is I want to do enough complex analysis so that you can solve integrals by contour integration. It's an incredibly powerful technique. How many of you know who Richard Feynman is? If you ever want interesting stories to read, you read his life stories. So he had a reputation for being able to integrate functions that no one else could integrate. And when people were stuck at MIT or Princeton, they would come up to him and he would solve it almost immediately. And what he says in one of his books is, look, the people coming up to me, they're not idiots. If you could have solved it using a standard technique, they would have. So I'm going to just assume they've tried all the common tricks and none of them have worked. And I'm going to just start off with the things that most people don't use. And so he would often do differentiating under the integral sign, which is a wonderful technique. And he would just immediately get a lot of problems just like that. So we might do that later in the semester. What I want to do is I want to do contour integration. It's a way to convert finding integrals to finding one specific term in a generalized Taylor series. Integration is hard, right? Calc 2 is the class of the big lock. You think you can do integration, you can't. We have to work really hard to give you functions that have closed form antiderivatives. And when you get to higher dimensions, it's even worse. Contour integration allows you to convert certain integrals to basic algebra. And I think this is what's needed to solve the problem that arose in a research project I was mentoring, so that after today, I think you will have enough to do it. There was a small typo in the problem that I gave you. The exponent should have been 2n and not n by the first assignment. All right, so here's the first theorem, that if I integrate r e to the I theta to the n ir e to the I theta d theta, this is 1 if n is -1 and 0 otherwise. So what we're doing is we can write z as x plus iy. We can also write z as r e to the I theta, where e to the I theta is cosine theta plus I sine theta. How many people has anybody not seen e to the I theta is cosine theta plus I sine theta? This is not always covered in classes. Okay, so one way to see that e to the I theta is cosine theta plus I sine theta is look at the Taylor series for e to the u, look at the Taylor series for cosine of u, look at the Taylor series for sine of u, and then plug in u equals I theta. And when you look at the Taylor series for e to the I theta, you'll see that it equals the Taylor series for cosine u plus I times the Taylor series for sine u. What this tells us is that there is a relation between trig functions and exponentials. So the exponentials, e to the a plus b is e to the a, e to the b. It turns out trig identities, the double angle formulas, the angle addition formulas, they're all inherited from the exponential function. So this is an incredible, amazing connection. So let's say I want to do this integral. Well, when I'm trying to do this integral, the first thing I can do is I can pull out the r's and the i's, because I'm just integrating over theta. So the I cancels. I get an r to the n plus 1 over 2 pi. That's horribly written. And I have an integral. Theta goes from 0 to 2 pi. Then I have an e to the I n plus 1 theta d theta. So this is r to the n plus 1 over 2 pi. Integral theta goes from 0 to 2 pi. And I'll write it out slowly. Cosine n plus 1 theta plus I sine n plus 1 theta d theta. And this should remind you of stuff we saw when we talked about the Goldbach problem and when we were integrating sines and cosines. So if you integrate cosine or sine over a full number of periods, what do you get? 0. So the sine term is always going to be 0. For the cosine term, there's one situation we have to be careful about when we don't have an integer number of periods. What's that one situation? Yeah. Yeah, if n equals -1, then I have the cosine of 0. What's the cosine of 0? 1. So if n happens to equal -1, then I'm integrating the function 1 from 0 to 2 pi, so I get 2 pi. Okay, the 2 pi would then cancel with the 2 pi down here. And because n equals -1, I would get r to the 0. This will collapse, and it becomes 1 if n equals -1 and 0 otherwise. So that finishes the proof. So this is the proof that this integral is equal to 1 if n equals -1, 0 otherwise. Why is this important? Well, I said z is x plus iy. What we really have is that integral is essentially the same as this. So if I write z as, z naught plus r e to the I theta, dz would be r e to the I theta I d theta if z is on a circle of radius r centered at z naught. So what's going on is, I have my point z naught over here, And then I have a circle centered at Z naught of radius r. And so how can I write a point on a circle of radius r centered at Z naught? I can write it as Z naught plus r e to the I theta. If we're centered at the origin, what would Z naught equal? Z naught would just be, zero. So this is just extending things a little bit. What if your circle is not centered at the origin? Well, then instead of integrating z to the n, I'm going to integrate z naught to the n. So if I look now, z minus z naught to the n is going to be z naught plus r e to the I theta minus z naught to the n. This is r to the n e to the I theta n. Or maybe n theta. I'll do n theta. And the other one, dz, is going to be r e to the I theta I d theta. So the integral is going to just be 1 over 2 pi I integral theta goes from 0 to 2 pi. And when I put things in, I'll get r to the n e to the I n theta I r e to the I theta d theta. And if you look, that's exactly what we had a moment ago. The only difference is, I guess a moment ago, I didn't distribute the n with the r e to the I theta. So this integral, which is 1 if n equals -1 and 0 otherwise, it extends immediately to this setting. If I integrate z minus z naught to the n about a circle of radius r centered at z naught, then I get 1 if n equals -1 and 0 otherwise. It's the same calculation. So this is one of the common techniques in integration, is you prove something in one setting and then you do a change of variables and then it holds in that setting as well. If you notice there's a circle around the integral, that circle is just notation to tell us it's a closed curve. You return to where you start. So we can now integrate z minus z naught to the n about a circle centered at z naught. Okay, so the next thing is, this is the big theorem. So imagine f is a meromorphic function. So what meromorphic function means is it's mostly differentiable. It can have finitely many places where it blows up. Now, I don't want to worry too much about it. So we have a function that's differentiable almost everywhere. It can blow up in a few places. And then let's say it has an expansion about a small circle of radius r about z naught. So we'll write it as, an z minus z naught to the n. So everyone has seen Taylor series before, correct? Have you seen Lorentz series? This is where you can have negative coefficients in the Taylor series. So if you have negative coefficients, we call that a pole. And so we will assume our functions have only finitely many negative coefficients, that it doesn't go off to infinity in that direction. You can, of course, handle a lot of obstructions like this. This is a 50-minute blitzkrieg complex analysis introduction. There's a limit to what we can do. The goal is to do enough so we can do some research integrals and to just show you what the techniques are. And then basically it says, if our function f is not identically 0, if we choose r to be sufficiently small, there won't be any zeros or poles inside a circle of radius r at z naught, except at z naught. That essentially it's saying the zeros and the poles are isolated. You're not going to have a curve where the function is identically 0. It's a beautiful theorem. We don't have time to prove it. What's nice is, in all the applications you have to do in real life, all these nice conditions hold. We developed the general theory, but when you're actually applying it, I'm integrating over a circle or a rectangle. I have a nice function. It's 1 over 1 plus z squared. The zeros are at I and minus. I can easily check everything. So none of these are really harsh constraints. Then what it says is that the integral about a circle of radius r centered at z naught of f of z is equal to a to the -1, the -1 coefficient. And the proof is extremely straightforward if you don't worry about convergence. So we have the 1 over 2 pi I, the integral, z minus z naught equals r. F of z is going to be the sum an z minus z naught to the n dz. We have an integral of a sum. What do you want to do to the integral of a sum? So what will we do to the integral of a sum? Switch. So this is where you need some kind of Fubini's theorem. This is why I was talking about in an earlier class, when are you allowed to switch orders? If you can switch orders, the integral of the sum is. This is why you have a class that proves things like this. So I have a sum n greater than or equal to n naught, an integral z minus z naught equals r, z minus z naught to the n dz. But we know that the integral of z minus z naught to the n dz is equal to 1 if n is -1 and 0 otherwise. Oh, actually, for that, we want the 2 pi as part of that. Because there was when we did it on the previous slide, it was 1 over 2 pi I times that integral is equal to 1. So I should put my 2 pi I there. So this is just going to become a -1. So if I'm integrating a nice function about a small point, all I need is the negative first Taylor coefficient, and I've got the value. So for example, let's say, here's my real line, here's my complex line, and I have some point where it blows up. And I want to integrate about this point. All I need to know is what is the -1 coefficient about that point. If the -1 coefficient is 0, what must be true about the integral? It's 0. So if a -1 at z naught is 0, integral is 0. So in particular, if I integrate a function that doesn't blow up along a closed curve. So for instance, let's say these are the places where my function blows up. If I give you as a curve a circle like this, the integral over that circle would be 0, because the -1 coefficient there is fine. Okay. And so here is our result, again, that if I want to integrate, all I need to know is the -1 coefficient. So the next thing we want to do is, you've hopefully seen this with Green's theorem. Imagine I give you some strange curve like this. And let's say that the point of action is what's going on at the origin. I want to reduce to integrating along a circle centered at the origin. How many of you have seen Green's theorem where you do something like this? You come down. So I think it was a good place to draw it. I'll draw it over here. That's hard to see. So you come in like this. You come in like this, and then you come back out. You're making this kind of slit and doing Green's theorem. Okay. How many people have not seen the slit in multivariable calculus? All right. So, and this is being recorded. Okay. So this is a great way to evaluate a lot of integrals. So it turns out you can extend these results. You don't have to integrate over circles. If you have a region where the function doesn't blow up, it turns out the integral is 0. And so what I'm doing is new region. And so the new region, I've got a very small gap. Oops, I want to do it the other way. So here is my big, outside region. And then I've got this little circle on the inside. And so if I look at this curve now, and I will disconnect it over here, I now have a nice region. Okay. The one point where my function blows up is now no longer inside my curve. And so because it's no longer inside the curve, the integral over this curve over here is going to be 0 because it doesn't have any points where it blows up inside. So that's the big result. If the function doesn't blow up, then the integral is 0. Well, but it blows up over here. But that point is no longer inside the curve. Okay? And then what they do in multivariable calculus or complex analysis is you take the limit as this thickness goes to 0. So as the thickness goes to 0, you come in and then you go out in exactly the same line, but in the opposite direction. So what happens if you integrate along a path and then integrate in the opposite of the path? Cancels it out. So in the limit, you get that the integral over this whole thing is going to be 0. And so what you get is the integral over the outside let's see if I'm doing this the right way. I've got my curve oriented the wrong way. I apologize. It should be oriented this way because I'm coming in. I actually have to go around the integral in this direction. Sorry about that. So the integral over this whole curve is 0. As I take the limit as that gap goes to 0, I get the integral over the outside plus the integral over the inside equals 0. We like counterclockwise in math. We like to do our integrals with our region to the left. Does it have to be that way? No. But you have to choose one way. And so we choose to do integrals counterclockwise. So the outside is counterclockwise, the inside is clockwise. So we're doing the integral on the inside in the opposite direction. So the integral of the outside plus the integral of the opposite of the inside equals 0. So the integral of the outside equals the integral of the inside. And this is one of the big results in complex analysis, is that if we have one point where the function blows up, we can take any curve that bounds the region and reduce it to integrating over just a circle. This is why complex analysis is so powerful. We only have to essentially learn how to integrate over circles, semicircles, rectangles, and whatnot. We just convert everything to those shapes. If I give you a region, and let's say it has a couple of bad points, and I want to integrate over something like this, well, what I can do is I come down, integrate, and then come back. And I come down, integrate, and come back. And then I come down, integrate, and come back. So we can reduce integrating over the red to integrating over 3 circles about each point. So again, this is a fast lecture. It's meant to be a fast lecture. It's meant to just show you what's going on. But we can reduce integrating functions over closed curves to just integrating over a few key points. And so what you would get is 1 over 2 pi I, the integral over the closed curve gamma of f of z dz is equal to the sum of z k, let's do it this way, a sum over k of the residue of f at zk, where this is the negative first coefficient of f at the point zk. So you can reduce evaluating the integrals to figure out what's going on just at a few key points. So let's do an example. So let's say I want to integrate from -infinity to infinity of 1 over 1 plus x squared dx. It turns out we don't need complex analysis to do this. If you remember your trig, there is a nice antiderivative for 1 over 1 plus x squared. Does anybody remember which function has derivative 1 over 1 plus x squared? Arctangent. So this is just arctangent at infinity minus arctangent at negative infinity. If I replace the 2 with a 4, however, we no longer have a nice antiderivative. So let's look at our function. So the first thing is I need to come up with some function f of z that when z is real, when z equals x, is 1 over 1 plus x squared. So somebody who hasn't taken complex, what do you think might be a good choice for the function z, f of z? It should reduce to 1 over 1 plus x squared when z equals x. What's the natural thing to try for f of z?
1 over 1 plus z squared.
Yeah, 1 over 1 plus z squared. Where does 1 over 1 plus z squared blow up? So for what values of z is 1 over 1 plus z squared undefined? I and what else? Negative I. So it has poles at z equals plus or minus I. So here's I, here's minus I. And so what I want to do is I want to evaluate the integral along the real line. What I'll do is I'll go from minus r to r, and I'm going to take a giant semicircle like this. Okay. And so what we get is, if we call this gamma, 1 over 2 pi I, the integral over gamma of f of z dz is 1 over 2 pi I integral, x goes from minus r to r of 1 over 1 plus x squared dx plus the integral over the semicircle of 1 over 1 plus z squared dz. Does everyone agree that the integral over the whole, so we'll say top of semicircle, that the integral over the whole semicircle is the integral over the bottom plus the integral over the top? Well, the integral over the bottom is exactly what I want to study. That's going to just give me the integral of 1 over 1 plus x squared dx. Wonderful. I now need to figure out what is the integral over the top. Okay. Everybody comfortable with where we are so far? So I'm going to show that this part over here goes to 0. Well, this part over here, this is just equal to the -1 Taylor coefficient. Do I need it at I, minus I, or both? Just I. Only I is inside the region. So I will show this goes to 0. This is residue at I, and this is what we want. And this is how you can handle some really difficult real integrals. If instead of having 1 over 1 plus x squared, I had 1 over 1 plus x to the 4th, you could do that. So let's look at the different pieces. So for the first one, we have, here's minus r, here's r, and we want to integrate 1 over 2 pi I integral over the top of the semicircle 1 over 1 plus z squared dz. So we can write z as r e to the I theta. What's the range of theta? 0 to pi. So 0 less than equal to theta less than equal to pi. So dz is going to be r I e to the I theta d theta. Now what about 1 over 1 plus z squared? What is the largest? Whoa. Someone come back. What is the largest 1 over 1 plus z squared can be? So can somebody tell me how large is z on the top of this semicircle? If this is a semicircle, how large is the absolute value of z on the top of the semicircle? R. So how large is z squared? R squared. Now, how large can 1 over 1 plus z squared be? It has to be at least how big, or at most how big? What's an upper bound? How large could this be?
1 over x value of t squared minus 1?
Yes. So it is at most 1 over r squared minus 1. The worst thing for us would be if z squared, oh, interesting. It's showing something different. Okay, now it's showing the same thing as mine. It was just taking a while for it to zoom it. So the worst case for us is if z squared equals negative r, because then when you add 1, you're going to decrease the absolute value by the most. So we know 1 over 1 plus z squared is at least, I'm sorry, is at most 1 over r squared minus 1. Thus, our integral is going to be less than or equal to 1 over 2 pi times 1 over r squared minus 1. And what's the length of the arc? What's the length of the top? Pi r. So it's less than or equal to, the pi's cancel. We have 1/2 r over r squared minus 1, which goes to 0 as r goes to infinity. So as r goes to infinity, the contribution over the top tends to 0. We don't have to worry about that. So now what's left? We now have, here we go again. Here is my semicircle, and here's the point I, and my function is f of z is 1 over 1 plus z squared. So I need to write the Taylor series, and I need to get the coefficient of the Taylor series at I. All right, let's see if I can do the algebra. So f of z is 1 over z minus I, z plus I, right? And we want to do the Taylor series at I. Oh, good, we want things like z minus I. So I can write this as 1 over z minus I, and then 1 over z plus I. Well, I don't want z plus I, I want z minus I. All right, so I'll write this as, z minus I inverse, because that takes up less space. And I can write this as z minus I plus I plus I, right? So I can write this as 2I plus z minus I, right? I can pull out a 2I, and so I get z minus I inverse. I pull out a 2I, so I have a 1 over 2I, and I have a 1 plus z minus I inverse over 2I. Yes, thank you.
Is that the reciprocal one, the twain in the middle?
It's not? It is. It is, yes. All right, how do we expand something of the form 1 plus u inverse? So if I give you 1 over 1 plus u, how do you expand that? Geometric series. So this is going to be 1 over 2I, 1 over z minus I, and then as we start to expand it, I get 1. I've got a plus sign, so I've got to remember I want to write for my geometric series 1 minus r. So here, r is equal to negative z minus I over 2I. If I want to write it, so it'll become 1 minus z minus I over 2I plus dot dot dot. But it doesn't really matter. I only care about the -1 coefficient. This is already, because I multiply by a z minus I, this is going to give me the constant term. The next is going to give me the linear term. So this looks like 1 over 2I z minus z minus I inverse plus dot dot dot. So what's the residue? So this is the residue. So when we put all the pieces together, we get 1 over 2I is 1 over 2 pi I integral x goes from minus r to r of 1 over 1 plus x squared dx plus piece going to 0 as r goes to infinity. So now if we let r go to infinity, yields the following. So we multiply both sides by I, good, that kills that. Multiply both sides by 2 pi, and we get pi is equal to the integral from minus infinity to infinity of 1 over 1 plus x squared dx. And that is arctangent of infinity minus arctangent of negative infinity. We have just solved an integral that can be done if you happen to remember your trick. Well, if I give you, for fun, do the integral from minus infinity to infinity of 1 over 1 plus x to the 2n dx, we can generalize this. And we can now solve this when n is any positive integer. With a little bit more work, you can do 1 plus x to the 2n plus 1 dx. N is a non-negative integer. Why don't I want to integrate this from minus infinity to infinity?
Cancellation.
Not cancellation.
Yeah, so the semicircle integral is 0.
It's not that. So what would happen if I have an odd power and I go from minus infinity to infinity? It's not defined on the path of integration. On the real axis, the function explodes. There are sometimes things you can do to handle situations like that, but it's much harder. A lot of times we use stuff like this as probability distributions. And so these are extremely important integrals to do in probability to find normalizations. So the integral that I want people to do for the research project was something like the integral from minus infinity to infinity of sine, I think it was pi nu x over pi nu x to the 2n sine 2 pi x over 2 pi x dx, where nu is equal to 1 over n minus 1. So this is the integral I want you to try to solve. And my guess is, we can write sine of theta as e to the I theta minus e to the minus I theta over 2I. And you can convert these to exponentials. And then when you expand things out, you start looking at the Taylor series, it's only the negative one term that matters. You can do some changes of variables. If people are interested, I would choose, u to be pi nu x. That will make the term to the nth power look nice at the cost of making this one look a little bit messier. Well, I'd rather have the term to the nth power looking nice and just move some of that to the other. And so what you would get, this is an even function, so you can integrate from 0 to infinity and just double it. You'll get some kind of sum involving some coefficients. So we'll call it maybe, an, well, let's call it am. Depending on the n in the integral, then we'll have e to the maybe mz, something like that. There'll probably be an I in here. And then we'll be dividing by, some powers of z down here. And the hope is that when you have something like this, we can then say, well, look, if I have the power of z to the 5th here, then the only thing that's going to matter here is the z to the 4th term in the expansion, because I need to get a 1 over z. And so my feeling is that you might be able to actually solve this problem and convert it to some kind of combinatorial problem counting things. And so if people are interested, I am happy to talk with people how you would attack a problem like this. The goal for today's lecture, this is a problem-solving class, is I want to show you what's out there, and if possible, I want to connect with a lot of the math you've seen before. So this was a good chance to review multivariable calculus. What does it mean to be differentiable? What is Green's theorem? And then see, how do you extend this further? It is absolutely fine, and there will be no test questions where I'm asking you to do something like this. But for many of you, this would be the last time you take a math class, right? And so I have a responsibility that you must see certain things. And converting painful integrals to algebra, this is a wonderful thing to see. All right, so I will end on that. And so if you are interested in trying to do the problem, let me know.